So the Bode diagram of a second order system. Open loop transfer function for second order system g of s is given as kp upon tau square s square plus 2 zeta tau s plus 1. So this is equation number 1. So first step is to find the expression for amplitude ratio as a function of frequency and phase shift as a function of omega. So for this, put s equal to j omega into equation number 1. So we will get g of j omega, and that is equal to a complex number z, and this will be equal to kp upon tau square j omega square plus 2 zeta tau j omega plus 1. So this will give kp upon, and here the first term is tau square j square omega square. So this will be minus omega square. So finally we will have 1 minus omega square tau square plus j 2 zeta tau omega. So this is another complex number z1. So let's say in the denominator we have z1 equal to, in bracket, 1 minus omega square tau square plus j in bracket 2 zeta tau omega. So we can write this as kp z1 inverse, and this can be written as kp z1 z1 conjugate to the power to the. So finally we can write this as kp, and this z1 mod of z1 square will be equal to a square plus b square, and here we will have 1 minus omega square tau square whole square plus 2 zeta omega tau whole square, and the complex conjugate of Z1 will be 1 minus omega square tau square minus j 2 zeta omega tau. So this is the capital G of j omega, that is equal to Z. So the amplitude ratio can be given as the square root of the real part of Z whole square plus the imaginary part of Z whole square, and finally we will get Kp upon 1 minus omega square tau square plus 2 zeta omega tau whole square, and square root of this under root 1 minus omega square tau square plus the imaginary part of minus 2 zeta omega tau whole square. So finally we will get the amplitude ratio will be equal to Kp upon square root of 1 minus omega square tau square whole square plus 2 zeta omega tau whole square. This is the amplitude ratio, equation number 2. Similarly, the phase shift phi can be written as the argument of Z and the argument of capital G of j omega, and that is tan inverse imaginary part of Z upon real part of Z. So finally we will have phi will be equal to tan inverse in bracket from equation number, from Z equal to this, the imaginary part is minus 2 zeta omega tau. So this is the imaginary part is minus 2 zeta omega tau under root 1 minus omega square tau square whole square plus 2 zeta omega tau whole square. So this is the imaginary part. This is the imaginary part of z upon the real part of z. The real part of z is 1 minus omega square tau square upon 1 minus omega square tau square plus 2 zeta omega tau whole square. This is the real part of z, and this whole is the inside the tan inverse. So after solving we will get phi equal to tan inverse minus 2 zeta omega tau upon 1 minus omega square tau square. So this is the phase shift expression for the second order system, and this is equation number 3. Here we can say that the amplitude ratio is a function of omega as well as zeta, and this phi is also a function of omega and zeta. Let's assume that we have case A, zeta is greater than 1. So it means we have overdamped system. So in that case the amplitude ratio will be equal to as per the equation number 2. As per the equation number 2 we have so this is equation number 2. From equation number 2 we have this, and the phase shift will be as per the equation number 3. So in this case, let's say we have zeta is equal to 2 and zeta is equal to 2. So the amplitude ratio will become Kp upon under root 1 minus omega square tau square plus 2 to the 4 omega square tau square. This will be 16 omega square tau square. So 4 zeta equal to 2, we will have amplitude ratio will be equal to Kp upon under root 1 plus 15 omega square tau square. This will be equation number 2.1, and the phase shift will be equal to tan inverse minus 4 omega tau minus 4 omega tau upon 1 minus omega square tau square. This is equation number 3.1. So in this case, we have amplitude ratio equal to Kp upon under root this. So if we take the log, so we will have log tan AR will be equal to log tan Kp minus half log tan 1 plus 15 omega square tau square. So log 10 upon AR upon Kp will be equal to minus half log tan 1 plus 15 omega square tau square, and this will be equation number 3.2. So now let's plot the Bode plot for zeta equal to 2. So in this case, so now step 2, plot Bode plot for zeta equal to 2, in this case less than 1. Sorry, in this case it's a greater than 1, it means for the overdamped system. So first start with gain plot. Gain plot, it means AR upon Kp versus omega tau. So first find out the low frequency asymptote. So to find out the low frequency asymptote, let's put omega tends to 0. So when omega tends to 0, it means we have omega tau tends to 0, and from equation number 3.2 we will have log 10 A R by Kp equal to minus half log 10. So omega tau is equal to 0, so we have 1. So it means A R upon Kp tends to 1. So AR upon Kp tends to 1 is a low frequency asymptote. So second, to find out the high frequency asymptote. So high frequency asymptote. To find out the high frequency asymptote, we put omega tends to infinity. So when omega tends to infinity, it means omega tau tends to infinity. So from equation number 3.2 we will have log. So from equation number 3.2 we will have so here we will have log 10 AR by Kp equal to minus half log 10 1 plus omega square tau square. So when omega tau tends to infinity, it means omega square tau tends to infinity. So it's a very large number, so we can neglect the first term. So we will get minus half log 15 omega square tau square, and so here actually we did some mistakes. So from equation number 2.1, if you take log 10 AR, so log 10 AR will be equal to log 10 Kp minus half. Okay. When we have zeta is equal to 2, so the amplitude ratio will be Kp under root Kp upon under root 1 1 minus omega square tau square whole square plus 2 zeta omega tau whole square. So here zeta is equal to 2, so zeta equal to 2. So finally we will get here AR equal to Kp upon square root of 1 minus 2 omega square tau square plus omega square tau square whole square, and then plus 2 to the 4 omega tau whole square. So 4 square, that is 16 omega square tau square. So on simplifying we will get AR equal to Kp upon under root 1 minus 14 omega square tau square and plus omega tau to the power 4. So this is the amplitude ratio when zeta is equal to 2. So now taking the log 10, so taking the log 10, so log 10 AR will be equal to log 10 Kp minus half log 10 of 1 minus 14 omega square tau square plus omega tau to the power 4. So further we can simplify and write log 10 AR by Kp will be equal to minus half log 10 1 minus 14 omega square tau square plus omega tau to the power 4. So this is equation number this is equation number 3, 3. This is equation number 4. And the phase shift, so the phase shift, phi can be written as tan inverse minus 2 zeta omega tau upon 1 minus omega square tau square. So this is from equation number 3. So this is from equation number 3. So if you put zeta equal to 2 for a overdamped system, so we will have phi equal to tan inverse minus 4 omega tau upon 1 minus omega square tau square, and this will be equation number 5. So using equation number 4 and 5 with zeta value equal to 2, we can plot the Bode diagram for the second order system when zeta equal to 2. So now let's plot the Bode plot for second order system. So step 2, Bode plot for zeta equal to 2, means overdamped system. So in this case, we will use equation number 4 for the amplitude ratio versus omega curve. So for gain plot, that is AR versus AR upon Kp versus omega tau. So here we will use equation number 4 for the gain plot. So when omega tends to 0, so when omega tends to 0, it means omega tau tends to 0. So from equation number 4, from equation number so from equation number 4, we will have 0 and 0. So log 10 AR by Kp will be equal to minus half log 10 of 1, or we can say AR upon Kp tends to 1. So this is the equation of low frequency asymptote. So second, when omega tends to infinity, we will have omega tau tends to infinity. So in that case, so from equation number 4, we can write minus half log 10, and we can take omega tau to the power 4 common, and inside the bracket we will have 1 upon omega tau to the power 4 minus 14 upon omega tau whole square plus 1. So therefore this term will be 0, this term will be 0, so we will be having only this first term. So we will have minus 4 log 10 omega tau. So we have minus 2 log omega tau. So this is equal to log 10 of AR upon Kp, and that will be equal to minus half log 10 minus 2 log 10 of omega tau, and this is the equation of high frequency asymptote. So this is the high frequency asymptote with slope of minus 2. So next, at omega tau equal to 1. So when omega tau is equal to 1, so from equation number, so when omega tau is equal to 1, we will have minus half log of 10 1 minus 14 plus 1. So this will be plus, and this will be plus, this will be plus, this will be plus, this will be plus, and this will be plus. And this will be plus, this will be plus. So finally we will have log 10 of 16. So log 10 of 16 1 upon under root 16, and that will be equal to log 10 of 1 by 4. So therefore A R upon Kp when omega tau equal to 1, we will have 1 by 4, that is equal to 0.25. So this is when omega tau is equal to 1, the amplitude ratio by Kp equal to 0.25. So this is all information which will be required to plot the gain plot against the input frequency. So now for B phase plot, when zeta equal to 2. So again using the equation number 5. So again using the equation number 5, so for phase plot we will use equation number 5. So when omega is very small or omega tau tends to 0, so in that case the omega square tau square is very less. So in this case omega tau square is very less. So in this case we will neglect the square term, and we will have 5 will be equal to tan inverse minus 0, and that will be equal to 0 degree. So for omega tends to 0, the phase shift will also tends to 0. So this is the phase shift at the low frequency. So second, when omega tends to infinity, we will have omega tau tends to infinity, or 1 upon omega tau also tends to 0. So here we can write phi equal to 10 inverse. So omega tau tends to infinity. So omega tau tends to infinity, and this omega tau also tends to infinity. So we have very large numbers. So if we divide the whole expression by omega tau, so we will have minus 4 upon 1 upon omega tau minus omega tau, and that will be equal to 10 inverse minus 4, and this first term will be 0 and the second term will be minus infinity. So we will have 10 inverse 0, and this will be again this will be 180 degree. This will be minus 180 degree. So when omega tau equal to 1, in that case from equation number 5, so this will be equal to 1 and this will be equal to 1. So 5 will be equal to 10 inverse minus 1, so minus 1 upon 0, and that will be equal to 10 inverse minus infinity, and that is minus 10 inverse infinity. So 5 will be equal to minus 90 degree. So this is the phase shift when omega tau is equal to 1. So using this information, now we can plot the gain plot as well as phase plot. So now let's plot the gain plot. So here in the x-axis we have omega tau, here In the y-axis we have AR upon Kp, and when omega tau equal to 1, and this is when omega tau is 10, and this is when omega tau is 0.01, and this is again the phase plot. This is 1.0, this is 100, and this is 0.01, and this is omega tau on the x-axis, and this is phi. So we have in the upper plot we have AR upon Kp versus omega tau. In the lower plot we have phi versus omega tau. So now start with low frequency asymptote. So the low frequency asymptote, so when omega tau tends to 0, AR upon Kp tends to 1. So this will be 1. So this is the equation of low frequency asymptote. Low frequency asymptote. So the slope of this line is 0, and let's say this is 0.1, and this is 0.1, this is 0.01, and this is 0.001. Again, when omega tau is very less, so we have the angle is 0 degree, and when omega tau is infinity, we have minus 180 degree. So when omega tau is equal to 1, AR upon Kp equal to 0.25. So when omega tau is equal to 0, we have AR upon Kp equal to 0. When omega tau is equal to 1, so AR upon Kp equal to 0.25. So 0.25 will be somewhere here, and then so here we have so from omega tau equal to 1, the high frequency asymptote will intersect with the low frequency asymptote. So you will have high frequency asymptote with the slope of minus 2. So using this information, now we can plot the gain plot like this. Similarly, for the phase plot, when omega tau is equal to 0, the phase shift is 0. So when omega tau is infinity, the phase shift is infinity, is minus 180 degree. So when omega tau tends to 0, we have phase shift 0 degree. So when omega tau tends to infinity, we have phi equal to 180 degree. When omega tau is equal to 1, so in that case the phase shift is minus 90 degree. So in that case, so this is the phase when omega tau is equal to 1. So now we can plot the frequency plot like this. So this is for the overdamped case, right? So what happened when we have underdamped system? So when we have underdamped system, so in that case, so for underdamped, so for underdamped system, zeta is less than 1. So when zeta is less than 1, so the amplitude ratio versus Kp will be much greater than at omega tau equal to 1. So in that case, when zeta is less than 1, so when zeta is less than 1, we will be having AR greater than AR upon Kp greater than 1. So in that case, the only modification we will have, so in that case we will have the frequency response like this, or the frequency response like this. So when we have underdamped system, so the AR upon Kp versus omega tau, the gain plot will be shown like this. So this is when, let's say, beta is less than 1, and that is, let's say, this is 4.1, and this is 4 zeta is greater than, zeta is equal to 0.2, and this is 4 zeta greater than 1, zeta equal to 2, and this is 4 zeta equal to 2. And for the phase plot, we will be having the curve like this. So this way we can plot the Bode plot for the second order system, for the overdamped system as well as underdamped system. So for the underdamped system, we will have amplitude ratio greater than 1 in the gain plot, or in the phase plot we will have much steeper plot in the phase plot. So that's all for today. Thank you.